Today, we're doing a deep dive into a stack of expert engineering tutorials focused on mastering smart electrical schematic design. The goal here is to give you a shortcut to building intelligent, error-free circuits.
And, well, building from the ground up starts before a single line is even drawn. We have to talk about how you intelligently pull and organize your parts.
Right, because we're starting at the foundation. These modern catalog browsers are less like standard parts bins and more like a magically organized warehouse, where every single part inherently knows its exact, unique serial number.
That is a great analogy. The moment you pull a push button into your drawing, the software assigns it a digital barcode, like PB5.
So it's actively tracking that unique tag.
Exactly. It tracks it across massive multi-drawing projects to guarantee you never have duplicates. And what's fascinating here is that the global search instantly locates precise manufacturer parts.
Not just a visual symbol, then.
No, not at all. It queries a relational database to pull exact catalog numbers. And this database isn't limited to electrical components either. It houses full pneumatic, hydraulic, and piping and instrumentation, or P&ID symbol libraries.
Wow, okay. That makes total sense for the initial build. But let's be real, designs inevitably change.
They always do.
So if I need to slightly move a component to make room, won't I have to painstakingly redraw every single connected wire?
Well, in the old days, yeah. But because the system sees a wire as a mathematical relationship between nodes, it actively assists you with a technique called scooting.
Scooting? Wait, so I'm essentially just sliding a database node.
Precisely. When you slide a component to adjust your physical layout, the software automatically stretches the wires.
Without breaking the connections.
Right, the electrical connection never breaks. You can even copy or flip components to change their physical direction without destroying that underlying logic.
That is huge.
Yeah.
But wait, what if I literally rip out a component? Say I delete relay number 4 out of a sequential bank of 10. Doesn't that glaring numbering gap ruin my downstream sequencing?
It would if you had to rename everything manually. But the software has a retag tool.
Okay, how does that work?
You just run it, and it flawlessly reorders all your component tags sequentially across the active drawing. It dynamically closes the gap so your numbering is perfectly accurate.
With no manual auditing. That is incredible. But here's where it gets really interesting, because, moving one part is easy, but handling the complex system physics is the real nightmare.
Exactly. A schematic has to obey real-world constraints. The software acts as a real-time auditor, verifying electrical compatibility on the fly.
Wait, really? By calculating component loads against wire gauges?
You got it. If you try to push a massive load through a weak wire, it flags the mismatched ampacity right away, highlights it in red.
Oh, wow. So it won't even let you make the mistake?
Right. Then you just select the correct size, and the software auto-updates the wire layers to the correct gauge, like, say, a thick 500 kilomilliliter cable.
And it does that across the entire circuit?
Yep, the whole thing. It is an amazing professional workflow. And speaking of pro workflows, you can also save custom circuits to the icon menu for future reuse.
So you're building out your own customized quick access library.
Exactly. And if you need to rapidly insert multiple components, you just draw a fence line across the wires and choose Keep All, Don't Ask to bypass all those repetitive dialog boxes.
So what does this all mean? It means these tools are turning tedious drafting into smart engineering for you. You're no longer just drawing lines, you're managing a living database.
Yeah, you define the logic, and the system manages the busy work to prevent human error.
Which leaves you with this to think about. If design software now automatically enforces real-world physics, calculates wire capacities, and maintains logical sequencing on its own, at what point does the software stop being just a drafting tool and start becoming an active co-engineer?
Welcome to today's deep dive, everyone. We are exploring the underlying architecture of AutoCAD Electrical.
Specifically looking at its advanced component libraries and customization capabilities. You have the NFPA symbols, which are based on imperial measurements, primarily inches.
Right.
And then you have the IEC symbols, which are based on the metric system, so measured in millimeters.
Now, you might assume, and I certainly did at first, that the software just, takes a single generic push button icon and scales it up or down, depending on whether you want inches or millimeters.
Which would make sense intuitively.
Right, but that's not what happens at all. The software treats these as entirely separate dialects.
Yeah.
A push button in the NFPA library visually represents itself completely differently than a push button in the IEC library. The actual geometry of the shape changes.
Which is why the software actually forces you to set your standard at the project level before you even begin drawing.
It won't even let you mix them up.
No, it won't. Because if you try to drop an IEC symbol into an NFPA drawing, the software doesn't just give you a symbol that's the wrong size.
Right.
It gives you a symbol that a North American engineer might misinterpret entirely.
Oh, wow. Yeah, that could be dangerous.
Exactly. So by setting the global standard, when you access the icon menu to insert a component, the software automatically filters out the wrong dialect and only pulls from the correct regional library.
Okay, let's unpack this, because getting the right symbol onto the digital canvas is really just step one.
Barely scratching the surface.
Right. The real shift happens the second that symbol hits the page. Because these aren't just digital stickers. I like to think of them as smart objects in a massive spreadsheet.
That's a great way to put it.
Yeah, they have a built-in intelligence that actively tracks their own identity.
And the mechanism behind that intelligence is a specific tagging formula built into the software's architecture.
The %F and %N thing, right?
Exactly. It relies on those two core variables. The %F is the family code string. So if the database recognizes the geometry of a push button, it assigns the %F as PB.
PB for push button makes sense.
Right. If you insert a control relay, it tags it CR. A motor gets MTR.
And then the %N represents the sequential numbering. It's the unique identifier.
Yep.
So the very first push button you place on the canvas becomes PB1. The next one is PB2. But the automation here doesn't just look at the single page you currently have open, which is the crazy part.
Oh no, it sweeps the entire project registry.
Right, and that is critical when you remember that modern industrial blueprints aren't just one page.
No, they can be hundreds of pages long.
Hundreds of pages spread across dozens of distinct file directories. So imagine you are the engineer on a massive factory floor project.
Okay.
You have used push buttons, PB1 through PB4 on page 3. 2 weeks later, you open up page 87 and drop down a completely new push button.
You've totally forgotten what number you were on.
Exactly. But the software instantly queries the background database, sees that PB4 was used 84 pages ago, and automatically names this new component PB5.
That's so seamless.
It continuously checks this project-wide registry so a component's identity is never accidentally stolen or duplicated.
What's fascinating here is how this seemingly minor background process profoundly shifts the burden of work.
How so?
Well, in traditional drafting, the human engineer has to hold that entire sequential timeline in their working memory.
Right.
Or, more realistically, they have to constantly cross-reference a separate physical spreadsheet on their desk. Like, did I leave off at PB4 or was it PB5?
I can imagine that gets incredibly tedious.
It does. And by shifting that memory burden entirely to the database, you eliminate one of the most common sources of human error.
Which is huge for safety.
Exactly. Duplicating a component tag on a massive industrial blueprint isn't just an administrative typo. When that blueprint goes to the physical build phase, 2 different machines labeled PD4 creates a critical, potentially catastrophic safety failure.
Man, so the software acts as a failsafe before the engineer even realizes they need one.
Yeah, it really does.
So, okay, the component now has an intelligent identity. It knows it is PB5. The next step is observing how that intelligent component physically interacts with the digital wires on the page.
Right, the connections.
And this is where the system starts acting less like a database and more like a strict physics teacher.
Because merely placing the symbol geographically near the wire just isn't enough to make the circuit work.
You can't just slap it on the screen.
No, the component has to functionally integrate with the conductive path.
And to make that happen, you actually have to disable some of the standard drafting conveniences, like you turn snap mode off.
Right, which feels counterintuitive at first.
Yeah, you have to manually and precisely align the component's connection terminals right over the digital wire. And when you achieve that perfect alignment, the software executes this fascinating physical action.
It literally cuts the digital wire to insert the part.
It actually severs the line.
Yeah, and the mechanism there is crucial to understand. The digital wire isn't just a drawn line.
It's not just pixels.
Exactly. It is a data object representing a continuous electrical flow.
Right.
So when you place the component perfectly, the software splits that single data object into 2 separate entities and bridges them with the component's internal logic.
That is so cool.
It really is the digital equivalent of taking wire cutters to a physical copper wire, stripping the ends, and screwing them into a physical switch.
And if that digital cutting action doesn't occur, the component is just floating there visually, right?
Yep. Electrically, the circuit is dead.
Wow. And the software's physics engine gets incredibly finicky when you move to 3-phase components.
Oh, absolutely.
Think of a a 3-pole breaker that needs to connect across 3 parallel wires simultaneously. The internal terminal spacing on the component has to match the spacing of the 3 wires on your screen.
And the software has a very specific directional quirk here.
Yeah, it is rigid, but it understands the physical reality of how copper wire bends. So if the internal spacing of your 3-phase component is slightly larger than the spacing of the wires you are dropping it onto, the software auto-adjusts.
It forgives you.
Right, it says, okay, the physical wire can easily flare out a bit to reach these terminals, and it snaps perfectly into place.
But if it's smaller?
Yeah, if a component's internal spacing is even a fraction of a millimeter smaller than the wire spacing, it outright refuses to connect.
And the reason it fails to attach is because, in the real world, forcing wider wires into a narrower terminal block creates a high risk of those physical wires touching and shorting out.
Oh, so it's a literal safety check.
Exactly. The software forces you to maintain safe physical clearances. But an even stricter rule it enforces, one that truly separates it from basic drawing tools, is strict directionality.
Okay, wait, why can't I just stick a motor pointing left? Or pointing straight up?
People ask this all the time.
I mean, if this is my digital canvas, why is the software restricting my freedom to place a shape wherever I want?
Well, if we connect this to the bigger picture, it comes down to enforcing a universal industry standard grammar.
A grammar for drawings.
Right. In schematic design, power inherently flows from the supply source toward the load.
Okay.
Visually, across the entire engineering world, that translates to flowing from left to right, or from top to bottom.
So it's like reading a book.
Exactly.
Mm-hmm.
If you place a motor pointing to the left, you are visually implying that power is flowing backward against the established convention.
So it's actively stopping me from drawing something that might technically function, but would deeply confuse the next engineer who has to read the blueprint.
Precisely. The software restricts your graphical freedom to guarantee your schematics are universally readable.
Which is so important.
It is. If you have a highly unusual circuit layout and you absolutely must have a section moving upward or to the left, you cannot just drop a component down backward.
It won't let you.
No. You have to physically use the software's rotation tools on that entire section of the circuit. The underlying flow logic must remain intact. The drafting is forced to match the physics.
It's an incredible layer of discipline. But, placing one motor perfectly, adhering to the flow logic, and hitting the exact wire spacing is manageable for a single component.
Sure, for one or two.
But in the real world, you are dealing with massive scale. You can't be painstakingly aligning components one by one for thousands of parts. You need mass automation.
Which brings us to the multiple insert capabilities.
Yes.
To understand this, imagine a standard electrical drawing layout called a ladder. You have 2 long vertical power rails running down the page, and horizontally connecting them are dozens of individual wire rungs, looking exactly like a ladder.
Okay, got it. If you need to drop a control relay on every single one of those 20 horizontal rungs, doing it manually would be agonizing.
It would take forever.
This is where a feature called the fence tool changes the game entirely. Instead of clicking 20 individual wires, you activate the multiple insert command, select your relay, and then you just draw a single diagonal line, a fence, straight down across all 20 rungs.
And the software executes a mass intersection query. Everywhere that fence line intersects a horizontal wire data object, it drops a component perfectly, automatically cutting the wire and applying the sequential tags.
It's like magic. But there is a catch.
There's always a catch.
By default, the software's safety protocols will trigger a pop-up editing dialog box for every single component it drops.
Because it wants you to manually confirm the tag and catalog details.
Right. So if you cross 20 wires, you are hit with 20 pop-ups, which completely ruins the efficiency.
Totally. To bypass that, you have to engage the system's batch processing logic.
Yeah, you select a specific toggle called Keep All, Don't Ask. This command suppresses the pop-up dialog entirely.
Thank goodness.
I know. You draw the single fence line, and instantly, 20 perfectly aligned, sequentially numbered relays are injected into the ladder.
So satisfying.
But placing the symbols rapidly is really only half the battle, because a tag that says PB5 is helpful for tracking, but it tells the procurement team absolutely nothing about what to actually buy to build the machine.
Yeah, the purchasing guys need part numbers.
Exactly.
This is where we bridge the gap between abstract geometry and tangible hardware using the global catalog browser.
Right.
You can search across real-world manufacturers. The system supports major providers natively. and assign real physical catalog data to these digital symbols.
You are injecting real-world specifications into the %F and %N tags.
Exactly.
Here's where it gets really interesting. Once you link that manufacturer data, the software can start doing the heavy engineering math on your behalf.
And my favorite part.
It's so cool. Imagine you drop a generic motor symbol onto your wire. You open the catalog browser and tell the software, hey, this isn't just a generic shape anymore. This is a specific 50 horsepower motor from this specific manufacturer.
And the moment you make that assignment, the database queries the manufacturer's specifications.
It just pulls it all in.
Yep. It pulls the motor's full load amperes, its operational speed, its thermal limits, and it applies those metrics to the circuit you've drawn.
And it triggers a specific background mechanism. It recalculates the wire size. Automatically. The software analyzes the load requirements of the 50 horsepower motor you just assigned. It checks the safety and ampacity requirements, and it might realize, the generic wire you drew cannot handle this electrical load without overheating and melting.
Right.
So automatically, without you clicking anything, it upgrades the wire layer for all 3 phases feeding that motor. It instantly changes the digital lines to represent thick, heavy-duty 500 kml wires, which, for you listening, is a massive, incredibly thick gauge of cable used for heavy industrial loads.
The physical properties of the wires are dynamically reacting to the power demands of the load they're connected to.
The wires are literally listening to the motors. Think of the hours saved here.
Oh, hundreds of hours.
You no longer have to manually cross-reference heavy technical code books to calculate the correct wire gauge every single time a client decides to, upgrade or swap a motor midway through the design process.
It emphasizes a core principle of modern design. Knowledge and data are most valuable when they are seamlessly, instantly applied.
Yes.
By integrating the manufacturer's equipment spreadsheet directly into the drafting interface, a single visual change instantly updates the safety parameters, the material bill, and the physical viability of the design.
It's all connected.
It completely eliminates the dangerous disconnect that occurs when a visual drawing says one thing, but the required physics demand another.
It transforms the schematic into a living ecosystem.
Yeah.
But as we know, no design survives its first contact with reality.
Definitely not.
Every project requires revisions, tweaks, and total overhauls. And this is where this highly automated, tightly interconnected database can actually become incredibly chaotic.
Very quickly.
If you change one small piece without understanding how the database manages relationships, you can accidentally break the entire system.
Right. Managing revisions is where the strict rules of the architecture become either your greatest asset or a massive source of frustration.
Depends on how you use it.
Entirely, depending on whether you respect the software's specific workflow.
So let's look at the simple act of moving a component an inch to the right. In a standard drawing program, you just click the shape and drag it.
Simple enough.
But here, the software forces a critical structural distinction between 2 commands. You have move component and you have scoop.
The vocabulary is deliberate there too, because the underlying database operations are entirely different.
Right. If you use the move component command, you are telling the database to sever the physical connection. You are literally ripping the component off the digital wire. The software will helpfully heal the wire behind it, closing the gap. But your component is now electrically dead.
Right, it's just floating again.
But if you use the scoop command, the database understands you want to maintain the circuit. It slides the component along the axis, dynamically stretching, dragging, and adjusting all the attached wire objects with it. The electrical integrity remains perfectly intact.
It's the mechanical difference between unplugging a device to move it versus sliding a device smoothly along an electrified track.
That's a great analogy.
But the true complexity of editing emerges when we look at how the database manages components that are geographically separated but physically united. This is the parent and child web.
Right, because a lot of industrial hardware isn't just one single box you drop on a page. A massive control relay, for instance, has a primary magnetic coil that receives power, but it also physically throws multiple different switches or contacts located throughout the machine.
Right.
The software manages this by designating the primary coil as the parent device and all the associated switches as sibling or child components.
And they share the same intelligent tag, perhaps CR1. Even though the parent coil might be drawn on page 1 of the schematic, and a child contact it controls is drawn all the way over on page 40.
And that invisible web completely dictates how you edit them. If you try to use a basic copy and paste command on the visual shape of a child contact, You're only copying a sibling. You aren't copying the main brains of the operation.
No, you're just drawing a meaningless shape.
Exactly. You have to explicitly dive into the database and link new parts back to a specific parent so the software knows they physically actuate together. But the real drama happens when you start deleting things.
Oh, deletion is where the database actively fights against human oversight.
Because if you decide to delete a parent relay coil from page 1, the software immediately intervenes. It throws a hard stop warning, essentially saying, hold on, this parent has children.
Think of the children.
Right. It prompts you, asking if you want the database to automatically sweep the entire 200-page project registry to find and eliminate its orphaned child components.
Because if you bypass that sweep and just delete the parent, you create a profound logical paradox in your blueprint.
So what does this all mean?
This raises an important question about data integrity in an era of information overload. Imagine you ignore the warning. You delete the parent coil on page 1, but you leave the child contact sitting on page 40.
Okay, bad move.
When the machine is built, the physical blueprint still tells the electrician to wire a contact on page 40. But there is no longer a physical coil in the real world to ever generate the magnetic force required to close it.
Right, so what happens?
The contact will float uselessly. The machine simply won't turn on. Human oversight across hundreds of pages is guaranteed to fail eventually.
For sure.
The software acts as a mandatory guardrail, forcing you to confront the ripple effects of your revisions so the fertile physical build actually works.
And beautifully, the database also cleans up the structural mess left behind by those revisions. Say you go through and delete several outdated breakers, like CB3, CB4, and CB5.
Yeah.
Now your sequential numbering is completely fractured. You have CB1, CB2, and then it skips all the way to CB6.
A fractured sequence like that is an absolute nightmare for a maintenance crew trying to troubleshoot the physical panel 5 years later.
Exactly. But you don't have to manually click and rename hundreds of subsequent breakers. You deploy the retag tool.
Oh, the retag tool is a lifesaver.
When you execute this command, the software initiates a comprehensive sweep of the project. It identifies the missing integers in the database array, recalculates the entire sequence, and pushes dynamic visual updates to the graphical layer. It instantly shuffles all the identifiers, turning that broken 1-2-6 sequence back into a flawless 1-2-3 progression across every single page.
It restores absolute order to the database architecture.
And it has brilliant rapid-fire tools for immediate physical tweaks, too. If you drop a push button that is normally open-like, a button you press to start a machine, but you realize the circuit actually requires a normally closed start button.
You don't have to delete it and start over.
Exactly. You don't go back to the catalog. You just click the toggle tool and tap the button. The software instantaneously flips its functional state in the database and visually redraws the symbol on the page.
That's amazing.
Or the dashed line tool, which lets you click two completely separate components on the screen and instantly links them with a visual dashed line, communicating to anyone reading the print that these two items physically interact.
Every single command we've discussed is ultimately about ensuring the visual communication on the screen perfectly aligns with the underlying physical data.
It is entirely about harmony between what you see and what the computer knows. So to bring all of this together for you listening, mastering a complex system like AutoCAD Electrical is clearly not about memorizing where the drawing tools are hidden in the menus.
No, it requires a fundamental paradigm shift.
Yeah.
You have to understand the underlying logic of the environment itself.
Once you learn to speak the software's native language, once you internalize how parent components dictate the actions of remote children, how dynamic wire layers actively listen and respond to the physical loads you place on them, and how a project-wide database actively intercepts and eliminates human memory errors, you realize you aren't really drafting anymore.
No, you're building.
You are constructing a highly sophisticated, living simulation of reality that merely happens to look like a drawing on a screen.
It forces a level of structural discipline that ultimately bridges the gap between digital theory and physical execution. And that leads to infinitely safer, more reliable, real-world systems.
And recognizing just how intelligent this underlying database already is leaves me with one final, slightly mind-bending thought for you to chew on.
Oh, what's that?
Well, we've seen today that the architecture already houses comprehensive real-world component catalogs. It already deeply understands the strict physics, clearances, and directional rules of electrical power flow. It can even actively recalculate and automatically deploy the exact material upgrades necessary based on the specific load of a parent component.
The foundational building blocks of complete design autonomy are already actively functioning within the code.
Precisely. So, how long until we aren't manually placing these symbols on the canvas at all?
Oh, wow.
Right. If the database already knows the physics, the safety regulations, and the exact specifications of the hardware, how long until we just open a text prompt and type, give me a 3-phase motor control circuit, 50 horsepower, with emergency stop functionality?
And it just builds it.
Yeah. And the software simply queries its own database, enforces all the real-world physics rules, and generates the optimal, perfectly tagged, flawlessly sequenced blueprint entirely on its own.
I mean, we are rapidly accelerating from computer-aided design toward purely computer-generated engineering.
It really makes you wonder what the digital canvas is going to look like tomorrow. Until then, keep questioning how your tools actually work, and we'll catch you on the next deep dive.